Hello everyone. To prepare for logistic regression in week 5, I'd like to take this opportunity to review some of the math and epi concepts that you already know. Okay, so for today, I'm going to first review the odds ratio from your epi course. Next, review exponents and natural logarithms. Then I'll introduce simple logistic regression, and then we'll look at how to do this in SPSS, and then I'm going to bring together the odds ratio that you learned about in epidemiology with the SPSS output and bring it all together so you can see it's all one and the same thing and to see how they relate to each other. Okay, so just to recap the odds ratio, we will be using data from the Titanic.sav dataset that you can find in Canvas. For this step, I have created the tables that we will be using. If you need to do this yourself, you can do crosstab gender multiplied by serve new, and I can show you how to do that later. However, you don't need to do this at this time because that's not needed for this first recap. Okay, so you recall in EPI, you set up your 2x2 table to look something like this. So first you have the exposure on the left. Here is female and male on the left. And then across the top, you have your outcome, yes or no, for survival. Okay, so here we can see that the females who survived, the total was 339. The females who didn't survive, the total was 127. Among the males, those who survived, the total was 161, and those who did not survive, the total was 682 for males. And so now I'm going to pause. I'd like you to pause this video and calculate the odds of survivals the odds of survival for females, and then the odds of survival for males, and then calculate the odds ratio of survival for females compared to males. Okay, so now that you've completed your answer, I'd like you to check your response. So remember, when you're calculating the odds ratio of survival, you have 4 columns, four cells in the table. You have the A cell, females and survived yes. The B cell, female and did not survive no, that's 127. The C cell, male and survived yes. C cell, and then the D cell, males and did not survive. So first, we're going to show how to calculate the odds of survival among females. So the odds of survival among females is A over B, and that's 339 over 127, and that gives you 2.669. The odds of survival in males is C over D, which is 161 over 682, and that gives you 0.236. So to calculate the odds ratio of survival comparing females to males, you divide the odds of survival in females by the odds of survival in males. So again, the odds ratio of survival comparing females to males is the odds of survival in females divided by the odds of survival in males, which is 2.669 divided by 0.236, and that gives you 11.31. So to interpret this result, you might say the odds ratio of survival comparing females to males is 11.31. Or you can say the odds of survival among females are 11.31 times the odds of survival among males. Okay, so again, typical stuff, what you used to do in EPI. getting the odds ratio. If you learned the cross product rule and odds ratio is AD over BC, you get the same thing. So AD, you would do 339 multiplied by 682 divided by 161 multiplied by 127. That's AD over BC, and you get the same number, 11.31. Okay, so again, that's the standard odds table. Oh, I'm sorry, that's the standard odds ratio from a 2x2 table. Okay, so the same thing can be done using logistic regression in SPSS. But first, we're going to review some basic rules of exponents and logarithms. So let's talk about natural log, sometimes called ln, sometimes ln, and exponents. So these two are inverse functions of each other. And what do I mean by that? Okay, so for example, if you have ln of y, the function of y, and that's equal to z, then it means that y equals exponential of z. Okay, it's e to the z. So again, if ln y equals z, then y equals e to the z. And so as an example, if ln y is 3, then y is e to raised to the power of 3, which is 20.086. Okay? So I'm going to substitute z with a plus bx. Okay? So then we say if ln y is a plus bx, then it follows that y equals e raised to the power a plus bx. We're going to refer to this as concept 1, and we will return to it later, okay? So when you think about concept 1, just think if ln of y equals a plus bx, then y is e raised to the power of a plus bx, okay? All right, so next I want to quickly review some of the rules of exponents, and there are 4 rules that you need to know. The first one is the product rule, okay? This rule says e raised to the power of n multiplied by e raised to the power of m is e raised to the power of n plus m. What that means is that when you multiply exponents with the same base, you add the powers. Okay, so here's an example. If you have e raised to the power of 3 multiplied by e raised to the power of 4, then that's the same as e raised to the power of 3 plus 4, or e raised to the power of 7, which is 1096.63. Okay? The second rule is the quotient rule. And this says e raised to the power of n divided by e raised to the power of m is e raised to the power n minus m. And what that says is when you divide exponents with the same base, you subtract the powers. Okay, so then that means e raised to the power of 5 divided by e raised to the power of 3 is e raised to the power of 5 minus 3, or e raised to the power of 2, which is 7.39. Here are a couple of other rules which will come in handy. The next rule is the 0 rule, which says e raised to the power of 0 is 1. And that applies to anything raised to the power of 0, and that's 1. Okay? And then the final rule says anything raised to the power of 1 stays the same. And so that means e raised to the power of 1 is e. Okay, so these rules will come in handy when we do logistic regression, so I wanted to review them quickly. So some practice questions on the rules of exponents. I'd like to do each one. For instance, you do this question and then pause the video And once you've done it and entered your answer in Canvas, then come back and check your response. So the question is, what is e raised to the power 2 plus 5x divided by e raised to the power of 5x? Pause the video now, write down your answer in Canvas, and then click continue on the video. Okay, so the answer here is e to the 2, and that's 7.39. Why? So the solution is as follows. E raised to the power 2 plus 5x divided by e raised to the power 5x is e raised to the power 2 plus 5x minus 5x, which is e raised to the power of 2, which is 7.39. Remember, in this case, the quotient rule applies, and that says e raised to the power a over e raised to the power b is e raised to the power a minus b. Here is another example. The question asks, what is e to the 2 plus 5x divided by e to the 2? So go ahead and pause this video now, enter your answer into Canvas, and then when you're done, you click play to continue. So here again, the answer is e to the 5x. So we apply the quotient rule as we did before, where e to the a over e to the b is the same as e to the a minus b. So again, we have e to the 2 plus 5x minus 2. That gives you e to the 5x. In this case, we can't evaluate fully unless we know what x is. But again, like before, we're using the quotient rule to divide two exponents with the same base. Okay, so now let's talk about logistic regression. Here we're modeling a dichotomous outcome. Okay, you will recall that linear regression models a continuous outcome. So if you have a dichotomous outcome, then you use logistic regression. So again, we use logistic regression to model a binary outcome. By that I mean a categorical nominal variable with two categories, usually 0 and 1. And 0 usually means the absence of the outcome, and then 1 usually means the outcome. Okay, so again, it's similar to what we did in simple linear regression, where we model the predictor in terms of an intercept and a slope. So if you remember, for linear regression, we had y equals a plus bx. So this a plus bx part is still the same for logistic regression. The difference in this case is that unlike simple linear regression, the outcome is not y. It's not a continuous variable, but it's ln of y, where y represents the odds of an event, where this event is a binary outcome or a binary variable. So examples include alive versus not, or cancer versus no cancer. So we have then ln y equals a plus bx. Remember, from simple linear regression, we have y equals a plus bx. Now we have ln y equals a plus bx. So y, again, in this case, represents the odds of survival, okay? And it's a binary variable. And a is the intercept, b is the slope, right? And then x is the gender. That's the variable that varies from individual to individual. X is gender, and then 1 equals female and 0 equals male. That's how it's been coded. So now our equation is ln y equals a plus bx. From concept 1 again, if ln y equals a plus bx, then it follows that y equals e raised to the power a plus bx. So if y represents the odds of survival, we can write ln odds of survival equals a plus bx. And that is also equivalent to the odds of survival equals e to the a plus bx. And now we're going to use that to model the odds of survival for a dichotomous exposure like gender, where male equals 0 and female equals 1. So again, modeling the odds of survival for a dichotomous exposure gender, x equals 0 for males and x equals 1 for females. Then back to our concept 1, we have that ln odds of survival equals a plus bx, which follows that the odds of survival equals e raised to the power a plus bx. So for females, x equals 1. So the odds of survival among females is e raised to the power a plus b times 1, which is e raised to the power a plus b. For males, x equals 0. So the odds of survival for males equals e raised to the power a plus b times 0, which is e raised to the power a. Okay, so now we're going to do this step in SPSS and see how the numbers compare and what. So for logistic regression in SPSS, we do analyze regression. So last week you learned all about linear regression. Now we're going to go to binary logistic regression. In this case, we're just doing a simple case and we're not worried about all the diagnostics yet, just a simple case. Again, analyze, regression, binary. Okay, and then so here you have the logistic regression dialog box. The first thing we're going to put is survived in the dependent box. And then where it says block 1 of 1, we take gender and drag it over. And then click OK. So then you will end up with an output that if you scroll down to the bottom, you'll get this table that says variables in the equation. So there's gender, there's a beta for gender, a B. There's the standard error, the statistic, the test statistic, the degrees of freedom, and the significance level. And then you have this term over here, which is exponential of beta, okay? Or exponential B, which is 11.307. Okay, does that ring a bell? All right, so here now I'm going to bring it all home. So recall that from our 2x2 table, we found that the odds ratio of survival comparing females to males was 11.31, okay? And so here is the table, again, the odds ratio of survival. So odds of survival in females divided by odds of survival in males gives you 11.31. That's the odds ratio. From SPSS, we also get this table. Exponential beta is 11.307. So again, that's the odds ratio of survival comparing females to males. And that's exactly that same number as 11.307. Okay, they're both the same. So you can see how you get that number from a 2x2 table. And also we showed how the odds ratio gets you to exponential beta, exponential b, which is that same term now for gender. Wow, isn't that cool? So I've just shown you simple logistic regression, how we go from the 2x2 table that we learned about in EPI, and then using some math that you learned way back in high school and logistic regression to get to how you get the output from SPSS. In real life, you would just go straight to SPSS, but I wanted to take the opportunity to show you how those two fit together. Okay, that's excellent. Don't forget to turn in your assignments in Canvas, and I will see you in class next week. Take care.